Okay, so good morning, everyone. Thank you for joining today's class. So I'm gonna explain to you about the last subchapter, which is subchapter 14.5 about the mechanical size reduction. Okay, yeah, so as you can see on the screen that there are two parts. So the left one is the Sean Copley's book. So I hope that you also open your book while listening to these courses. And the in the right hand side, like we have PPT here. Yeah, so you can see the course outline for today. Yeah, first is introduction, second is equipment for size reduction, third is the energy and power required in size reduction. The fourth one would be the particle size measurement. Okay, so we're going to introduction first. So actually, in industries, this solid size reduction process is actually one of the most commonly used processes. Yeah, let's say that we are working in a teh botol sosro, let's say, yeah. So we will extract the tea, yeah, from the tea leaves, right? Now, for the extraction, usually the tea leaves will be cut first, will be ground first, yeah, before it is subjected to the extraction process. So grinding and then cutting is actually one method to reduce the solid size. Okay, now solid can be reduced in size by several methods. Yeah, first is by compression or grinding. Yeah, so this type of method can reduce the hard solid, yeah, to coarse particle. Then we can also use method of impact. Yeah, it can reduce the large particle to coarse, medium, and fine particles. Yeah, so that's why usually by using the impact based machine, then we can actually also obtain the fine particles instead only coarse or medium size particle. Okay, and then we can also use the method of attrition of rubbing. Yeah, it may produce fine particles. And for cutting, yeah, it reduces particle size to a definite sizes. Okay, now the equipment for size reduction can be classified into several types, yeah, according to the way forces are applied. So first, between the two surfaces, yeah, as in crushing or shearing, yeah, and then at one solid impact, yeah, and then by action of the surrounding medium, as in mill, yeah. Okay, so I will go to the first equipment. Yeah, so the principle of the jaw crusher. So this is, we call it a jaw crusher because as you can see here, yeah, there is a jaw here. So it works like our mouth jaw. Yeah, if you see here. Yeah. So the principles is that the material is fed from the top, yeah, between the two heavy jaws or flat plates. Yeah, so this is the stationary plate. This is the moving plate that works like a jaw. Okay. Yeah. So one jaw is fixed, the other reciprocating jaw move, yeah, in the pivot point, yeah, at the bottom. Yeah. Or sometimes it can also move at the pivot point at the top. Yeah. So it can be like this. It can be like this. Okay. Okay. Now the reciprocating jaw, yeah, swings back and forth. Yeah, just like this. Yeah. It moves uh back and forth. Yeah, pivoting at the bottom of V. Yeah, so it shapes like a V. Yeah, the material goes down to the narrower part, yeah, of the jaw crusher will be crossed, yeah, as it moves. Okay, now the reduction ratio averages at about 8:1 for blade type. Yeah, so let's say if we have a very big, like 8 centimeters of solid particles, yeah, then it can be reduced at maximum 1 centimeter. Yeah, because it's 1:8. Okay. Now, jaw crusher is usually used for primary crushing, yeah, of hard materials, and then followed by the other type of crusher. Okay, so this is the first, the primary crushing. Yeah, the primary crushing for hard material. Yeah, and to make it smaller, yeah, to make the particles smaller, then usually this the result from this jaw crusher will be subjected into another solid size reduction. Okay, and then the second one is gyratory crusher. Yeah, so it's usually used in the field of large hard or mineral crushing application. So this gyratory crusher is usually used in the mining. Yeah, the ore mining. And the principle, yeah, is actually similar to mortar and pestle crusher. So if you see here, yeah, there is a movable crushing head, yeah, that is shaped like an inverted cone, yeah. It's like inverted truncated cone, yeah. Okay. Now, and then the solid comes from the top like this, yeah. The solid comes from the top. Okay. Now, and the crushing head, yeah, this truncated cone here moves, right? Rotates, yeah. Then the material that is trapped, yeah, between the fixed plate here, yeah, and here, yeah, and also the casing mill or the truncated cone here, yeah, that moves, yeah, will be gyrated, yeah, to form a smaller particle. So as you can see here, when it is released, yeah, here at the bottom, yeah, then you can get the finer particles, yeah. Okay, so this is the gyratory crusher, yeah. The sample comes from the materials is fed from the top, and then it goes down from the bottom. Yeah, and it has to pass this moving crushing head. Yeah, that looks like a inverted cone. Yeah. Okay. Now, and then we have also another type of crusher. Yeah. The principle, yeah, it usually consists of two rolls. Yeah, that rotate toward each other. Yeah, at the same or different speed. Yeah. Okay. Now, okay, it may also sometimes, yeah, only consist of single roll, but the other one is a fixed wall. Yeah. Okay, so the materials come from the top, and then because the two rolls rotate to each other, yeah, it also crush the material to become smaller. Yeah. Okay, now the type of roll, it can be the smooth roll, it can be the corrugated roll, it can be the toothed roll. Yeah, toothed roll is like a gear. Yeah. And then the reduction ratio range from 4 to 1 to 2.5 to 1. Yeah, so let's say like if we have 8 centimeters of particle coming in, then the maximum result, yeah, the minimum size that can be achieved is 2 centimeters. Yeah. Okay, now it's commonly used to reduce size of not so hard materials, yeah, such as flour. Okay. Now, and then one thing that we have to pay attention for maintenance, yeah, it's that the rolls can be wear off, yeah, can be worn off, yeah, and it's a serious problem because it will significantly decrease the efficiency of the plastic. Okay, and then yeah, so the previous one is crushing, yeah, it's crushing type equipment, yeah, and then for the impact type of equipment, yeah, one of them is hammer mill. Yeah, so it's usually used to reduce intermediate size materials to small size or powder. Yeah, so it's usually used after the crusher. Yeah, so like previously I told you that jaw crusher is actually the primary uh reduction machine. Yeah, for a very hard and big particle. Yeah, but after that we have to, if we want a smaller particle, then we have to submit it or we have to fed those results, yeah, to another solid reduction machine. Yeah, so and one of them is actually hammer mill. Yeah, so after jaw crusher, sometimes they will put it in the hammer mill as well to make it smaller. Yeah. Nah, okay, yeah. So this one is the statement, yeah, of the previous explanation. Yeah, that often the product from jaw or gyratory crusher is fed to this hammer. Okay, now the principle, yeah. So we have a vessel like this, yeah, and we have a high-speed motor, yeah, we have a motor here in the center, yeah, with a set of hammer, yeah, so we see there is hammer here, yeah, inside a horizontal casing, so we have a vessel, horizontal vessel, yeah, and then the feed is fed from the top like this, and then the material is broken, yeah, by the impact of the hammer. So it's just like it, yeah, we use the it solid, yeah. Now, and because of the impact with the hammer, then the material will be pulverized, yeah, into powder, yeah. Okay. Now, and then we have a grate or screen here, yeah, attached on the bottom, yeah, or we can say the outlet, yeah, to make sure that the size coming out from this machine is uniform. Okay, that's hammer mill. Now, okay, so we also have, aside for the hammer mill, we also have this rotating liquid mill. Yeah, so the principle of this is the attrition. Yeah, attrition. This one, sorry, this one. Yeah, the attrition of rubbing. Yeah. Okay. Yeah. So it's usually also, yeah, used for intermediate particle. Yeah. It's used for intermediate particle to be reduced in size to a fine particle. Yeah. So the principle, yeah, we have also a horizontal casing, yeah, or mill, yeah, and then we put a steel ball, yeah, steel rod, yeah, or a flint, ya. Jadi ini kalau teman-teman lihat, this is a ball, metal ball, ya, steel ball. Okay. So we put the steel ball inside, and then we put, yeah, we put the solid that we want to reduce the size inside the vessel. Okay. And then once the casing, the horizontal casing rotates, then there is a tumbling, yeah, between the steel ball with the solid. Yeah, and the metal ball will rub on the solid surface and make it smaller. Yeah, okay. Nah, okay, so yeah, this one, the third point. Yeah, the grinding elements, which is the steel rod, steel ball, or flint, yeah, are carried up due to the rotation. Yeah, and then fall on the particle underneath. Yeah, so it will reduce the size, and there is also a rubbing. Yeah, between the balls. Yeah, towards the solid particles. Yeah, so it also makes the solid particles smaller. Yeah, nah, okay. Now, the mills, yeah, this type of mills may operate in both wet or dry condition. Okay. Nah, okay, so we go to the energy and power required in size reduction. So the general theory of the size reduction is actually given by this equation on the left, yeah, equation 1 in subchapter 14.5. Yeah, where actually the change of energy to change the size of the particle, yeah, depends on the desired size that we want. Okay, where C here is constant, N is also a constant depending on the law later. Okay, now there are two laws, yeah, that is usually used in the size reduction process. The Rittinger is actually three. Yeah, three laws that is usually used in the size reduction process. The first one is Rittinger law. The second one is Fick law. The third one is Bond law. Okay. So this is actually the general equation, yeah, for size reduction. Yeah, so we have this dE over dx is the change of energy to change the size, which is depends on the desired size that we want. Okay, C and N is actually depends on the law that we use. Okay, it's constant. Okay, now, so for Rittinger law first, yeah, for Rittinger law. So Rittinger proposed that actually the energy or the work that is required to cross materials is inversely proportional to the new surface created. So the energy required to cross materials is inversely proportional to the new surface created. Yeah. Therefore, the n value here equals to 2. Yeah, since area is actually size or, this is not per, yeah, this is size or diameter to the power of 2. Yeah, so that's why n equals to 2. Yeah, so by integrating this equation 1, yeah, it will give equation 2. Okay, now, and then by substituting this value of n equals to 2 here, and also here, then we can actually get equation 3. Yeah, because c over 2 minus 1 is c, right? And then 1 over x2 to the power of n minus 1. N equals to 2, 2 minus 1 equals to 1. So it's 1 over x2 minus 1 over x1. Yeah, so the c here becomes kr. Yeah, kr is a constant, so it's similar to c. Yeah, yeah. So okay, so by knowing these two equations, yeah, and by putting n equals to 2, then we can get this equation 3. Okay, where x2 is size after crossing, x1 is size before crossing. Okay, so that's Rittinger law. Okay, so E is actually the work or the energy required to reduce a unit mass of it from x1 to x2. Yeah, so x1 before crossing, x2 after crossing. Okay, nah, okay, and then we have also the second law, yeah, called Kick law. Yeah, so Kick assume that the energy required to reduce the size of solid was directly proportional to the size reduction ratio. Yeah, therefore n is 1, and since it's not inverse, so it becomes like this. Yeah, so ln x1, sorry, so okay. Yeah, so sorry, it's directly proportional to the size reduction ratio. Oh yeah, correct. Yeah. So it's actually not directly proportional to the size reduction ratio, friends. Yeah. But it's actually inverse, yeah, because dE per dx equal to 1 over x, right? So it's still inversely proportional, yeah, to the size reduction ratio. But since it depends on the size, so therefore the n equals to 0. It's not depends on the area, right? Area is x to the power of 2, but since it's size, so x to the power of 1. Okay? Okay, so Kick assume that the work required in size reduction is inversely proportional to the size reduction ratio. Therefore, n equals to 1. And then the integration of this, yeah, it becomes equation 4. Yeah, why? Why? Because the n is equal to 1. So 1 over n. If we integrate that, it becomes ln, right? Becomes ln. Yeah, okay. So that's why it becomes ln x1 per x2. Yeah, and then the c, yeah, they change it to kk. Yeah, kk is a coefficient for Kick, kr is coefficient for Rittinger. Yeah, okay, so that's for the Kick's law. And then we also have the last law called the Bond law. Okay, yeah, so the Bond suggested that the work or energy required to reduce the size of a large size feed is inversely proportional to the square root of surface per volume ratio of the product. Yeah, therefore, yeah, surface over volume. Yeah, and then square root. Yeah, now therefore the n is equal to 1.5. Okay, therefore n equals to 1.5. Okay, now and then the same, yeah, we use the general equation, yeah, and then we integrate the equation and it will give equation 5. Yeah. Now, Bond final equation is actually equation 6 here. Yeah. where EI here, you see EI, this is actually the work index, yeah, the work index or the work required to reduce a large size particle, yeah, to 80% passing 100 microns. Yeah, so EI is a constant here. Yeah, okay. Yeah, while yeah, E or P here. Okay, so while E here, yeah, while E here, yeah, it's actually the gross work, yeah, it's the gross work to reduce 80% of it passing XF microns to products with 80% passing XP microns. Yeah, yeah. So after we combine, yeah, the two equation, yeah, and becomes equation 6, then we have P over P equals to 1.46 EI times blah blah blah. Yeah, now EI is the work index, yeah, so it's a constant, and then dP is actually the diameter of the product, dF is the diameter of the fit, yeah, T is the weight of the fit, yeah, per unit of time, yeah, but in this equation they ask us to use this unit, yeah, tons per minute, okay, tons per minute, and P is the power required, yeah, or the energy required. Okay, okay, some typical value of EI, yeah, can be seen here, yeah. Okay, let me try. Okay, so this is some typical value of EI, yeah, and this value, yeah, should be multiplied by 1.34 for dry grinding, yeah, for dry grinding. Okay. Yeah, because the power used for dry grinding is higher if than if we use wet grinding. Okay, nah, okay, and then we go to the particle size measurement. Yeah, nah, in industry, yeah, the particle size can be measured by using mass sieve, ya, massive, jadi kayak pakai saringan gitu ya. Nah, what is mass? Ya, mass is actually an empirical unit where it shows how many sieve opening in 1 square inch. Yeah, so you can actually see appendix 5.5. Let me try to go there. Nah, here. Yeah, here, mass. Yeah. Okay, so they said, oh, it's uh this one. Yeah, 2.5 mass, 3 mass. Yeah. It's actually an empirical unit where it shows how many sieve opening in 1 square inch. Yeah. So we can see here. So let's say, yeah. Oh, I have a sieve. I have a mass sieve with the size of 3 mass. That means the opening, ya, jadi lubang-lubangnya saringan itu, ya, itu memiliki diameter sebesar 0,263 inch, ya, or 6.68 millimeter. Yeah. Oh, I have a massive of 100 mass. Okay, so we put 100 mass. Then the opening, yeah, the opening diameter of the strainer is 0.0058 inch or 0.147 millimeter. Yeah. Okay. So mass here is an empirical unit where it shows how many sieve opening in 1 square inch. Yeah. So if 100 mass, that means in 1 square inch there is 100 openings. Ada 100 lubang. Yeah. For 3 mass, yeah, 3 mass here. Then in 1 square inch there is 3 opening. There are 3 openings. Ada 3 lubang. That's why the diameter of the opening will be higher increments as compared to 100 mass. Okay, so you can actually see it from here. Yeah, for the mask opening diameter. Yeah. Now another thing to you, another equipment to measure the particle size, yeah, is to use the zeta sizer. Yeah, or we call it as PSA. Yeah, particle size analyzer. Uh, so it's an instrument. Okay. Yeah. Okay. So I will go back to the page of the example one. Okay. Now. Okay. Yeah. So we are asked to calculate the power to crush iron ore by Bond's theory. Okay, so we go back to the Bond's theory here. Yeah. So we are asked. It is desired to crush 10 ton per hour. Yeah, 10 ton per hour of iron ore hematite, and then the size of the feed is such that 80% passes 3-inch screen, and 80% of the product is to pass a 1/8-inch screen. Okay, and then we are asked to calculate the gross power required. Yeah, use a work index of iron ore hematite of 12.8, 68. Yeah. Okay, so we know the feed size. Yeah, so this is the feed size, 3-inch. Yeah, 3-inch, right? So if I want to make it into feet, yeah, then I have to divide the 3-inch with 12. Yeah, so it becomes 0.25 feet. And then it goes as well for the product. Yeah, I have a product with passing this screen, passing this 1/8-inch screen. So that means that the product size is also 1/8-inch or 1/96 feet. Yeah, or this. Yeah. Okay. And then let me go up. Okay, let me see. Yeah, here. Yeah. Okay, so we know dP and dF. They said that both dP and dF, yeah, the unit are in feet. Okay, so we have it correct. And then the T here is feet rate in tons per minute, but here is ton per hour. So we have to change it to ton per minute first. So that's why they divide it with 60. So it becomes the 0.167 ton per minute. Okay, and then we are asked to calculate the power. So we put all of the known number here. Yeah, and we put 12.68 here. It comes from the problem. Yeah, it's EI of the hematite. Okay, so I get that the power is 24.1 horsepower. Okay, we see here the P is in HP. Yeah. Okay. Yeah. So if you have any question, just drop a message in the WhatsApp group. Yeah. And please also work on the problem of 14.5-1 and 14.5-2. Yeah. And then, so no, it's not submitted to Bella. Yeah. Submit it before the class. Okay. For the quiz. Yeah. The due date. Yeah. Okay. So submit it before the quiz. Yeah. The due date will be on June 5th. Yeah. Before the quiz. Okay. Okay. So actually, before the quiz, you have to submit 2 assignments. Yeah. Assignments for centrifugal separation and assignment for this mechanical size reduction. There are 2 assignments. Okay, so please don't forget to bring your assignments, yeah, prior to quiz, yeah, and submit it to me. Okay, thank you very much, and see you on June 5th.